Alright, so since we know that Fty equals 24.5 newtons, we can use that information as well as this angle to find Ft. So thinking back here, what we have is the opposite side relative to this 40-degree angle, this known 40-degree angle in a right angle triangle. And we need Ft. So we have the opposite, we need the hypotenuse. And if we look at the sine of 40, it involves both of those. It involves, so sine 40 is equal to the length of the opposite side divided by the length of the hypotenuse, which in this case means that sine 40 is equal to Fty divided by Ft. Which means that we can solve for Ft by rearranging this equation. Ft then, these are both vectors, Ft equals Fty divided by sine of 40 degrees. And so Ft then equals 24.5 newtons divided by sine of 40. And if we do that math, we get a figure for Ft of 38.12 newtons. And we also know that the other Ft, which was coming off in this direction, would also be 38.12 newtons because we decided that those two are equal because we made the assumption that that sine would slide freely along the cable. And next we're going to talk about moments. And moment is the force applied to a lever multiplied by its distance from the lever's fulcrum. A moment is otherwise known as a moment of torque. And so we can define a moment as m being the symbol for moment equaling a force times r, which is the distance from the fulcrum or the point of rotation to the place where the force is applied. And so r is the vector from the axis of rotation to the point on which the force is acting, and F being the component of the force vector acting perpendicular to r. And so let's solve a problem using moments. Here we have a beam which itself is massless, and a 1,000 Newton force acting down on the beam. This beam is supported at either end, on the left side by FL, on the right side by FR, but we don't know how much each of those are. We know that that together they're going to be equal to 1,000 newtons, but you'll notice that this 1,000 Newton force is closer to FR, and so FR really should be bearing more of that 1,000 newtons than FL is. So we know together they're equal to 1,000 newtons, but we don't know how that 1,000 newtons is split, although we do have a clue that FR is going to be higher than FL. And so in this case, let's take up as being positive. So FL and FR, these are positive, and this 1,000 Newton force is in the opposite direction, so let's call that negative. All together, those three forces will equal 0. That is to say, there's going to be no net force on this beam. Now we can move this 1,000 newtons over, and we can say that the up forces are equal to the down forces. So FL and FR together equal 1,000 newtons. Now, in order to get further than this, what we're going to have to do is develop another equation involving moments. And the way that's going to work is, just as here, where we said that this is in translational equilibrium, thus the up forces must equal the total of the down forces. With regard to moments, what we're going to do is say that the positive moments, that is, the moments causing a clockwise rotation, must be equal to the moments causing negative rotation. If those two are equal, then this is not rotating, and again, that's the assumption that we're making, that this is not going to be rotating in space. So just as before, where we said the up moments, the total of the up moments equal the total of the total of the up forces equal the total of the down forces, we're going to say that in this situation, the total of the positive moments, that is, the moments causing a counterclockwise rotation, equal the sum of the negative moments, the moments causing a clockwise rotation. Now, in order to calculate moments, because we need the distances between the point of rotation and where the forces are acting, we'll need to throw in some measurements. So we'll say that this distance is 2 meters, and this distance to the right of the downward force is 0.5 meters. Now, we said that we need the distance between the point of rotation and wherever any force acts, and this place where any force acts. Because this is not going to rotate, we can pick any place as a theoretical point of rotation and say that the moments causing positive rotation will equal the moments causing a negative rotation. Now, we could choose this point right here if we wanted to, this point right here. And then, in this case, FL would cause a negative moment, because that's going clockwise. This F would cause a negative moment as well, and FR would cause a positive moment. Now, we could do that. What we're going to do instead, though, is we're going to pick a point either here, or here, or here. The reason that is that if we pick this point here, then FL is acting at a distance of 0 meters from this theoretical point of rotation. Since it's acting at a distance of 0 meters, this moment will be 0, and that has the effect of eliminating FL from our calculations. So this simplifies our work a lot. It's still possible to choose any point along here, this one or this point here or this point here, but by choosing a point either here or here or here, we'll eliminate one of these variables from our calculation and make our lives a lot simpler. All right, since we can pick any point along this beam about which to take the moments, that is to say we can pick any moment along this beam to act as a theoretical rotation point, let's arbitrarily pick one and work from there. Doesn't matter which one we pick, but if we pick this one or this one or this one, then our calculation is simplified. So let's choose this point. All right, so taking moments about FL, so we're working about FL, we can say that the positive moments, the sum of the positive moments will equal the sum of the negative moments. Now, this here, this force here, relative to this point of rotation, will cause a negative moment. And this one here, FR, will cause a positive moment. So let's organize our moments that way. FR times a distance of 2 meters, 2.5 meters, because this distance here is 2.5 meters. That is from FR So our point of rotation is 2.5 meters. So Fr times 2.5 meters will equal 1,000 newtons times 2 meters. This 1,000 Newton force acts at a distance of 2 meters from the point of rotation. And so we can rearrange this to say that Fr equals 1,000 newtons times 2 meters over 25 meters. We have 2,000 meters divided by 25 then. Fr will be equal to 800 newtons because the units of meters cancel out. And that's of course 2.5 meters, not 25, which makes Fr equal 800 newtons. Taking that into our previous equation, where Fr plus Fl equal 1,000 newtons, we can see that Fl equals 1,000 newtons minus 800 newtons, because Fr equals 800 newtons, so we move that over, and Fl then equals 2